In statics, when you are working with 3D vectors, a very common thing you'll be asked to do is determine the force along a line. And this line can represent a rope or a cable. And especially when you start getting into 3D equilibrium problems, you're going to need to break up that force along a cable. So when we were working with 2D, 2D was a little bit easier. In 2D, because we only have two planes, if we have something with a weight and something with a cable, we know that cable force, the tension, would always act along the actual cable, and we could have some type of angle, or we could have some type of similar triangle, and we could break those into components that way and then solve for whatever we needed to solve for if we were doing a 2D equilibrium problem. In 3D in 3D vectors, the geometry usually isn't as nice. So those trigonometric type functions won't work, and we need to go about a different approach. So what we are going to do is we are going to use a vector equation. We're going to say that the force along a line is equal to the magnitude of the force times some unit vector. So let's just say this is some unit vector, and this is going to point from, in this case, we're going to go from A to B. So this is going to be our unit vector. This is going to be our force. And what we should notice is this unit vector is going to point along the same distance. Let me change the color, but it's going to point along the same distance that a position vector from A to B would point. So if this is our position vector from, let's call it A to B, the unit vector is along the same line, and we can rewrite this equation in terms of our position vector, because typically we'll know this point that B is at, we'll know this point that A is at, and then we can figure out what the position vector is. Now let's refresh our memory just a little bit. In general terms, if we have some vector A, it's equal to some magnitude times the unit vector of A. So if we rewrite this, and then we can solve for this unit vector dividing the magnitude of A by the other side. So if we rewrite this for a position vector, we're going to have our position vector, RAB, is going to be equal to the position vector, RAB, the magnitude of the position vector, RAB, times my unit vector, UAB. So I'm writing it in terms of this general case right here. Solving for this position vector, UAB, this is going to be equal to our position vector divided by the magnitude of the position vector. And this is what we are going to put into this equation right here. So our force, and this is a vector, is going to be equal to the magnitude of our position vector, RAB, divided by the magnitude of that position vector. And this is the equation that we'll use to figure out the force along a certain line. So this is going to be the force along a line. And now I want to solidify this with an example. In this example, we're going to be pulling on a rope with 30 pounds of force. Where we are pulling the rope, that's going to be 5 feet above the ground. It's going to also have this dimension of from our origin, which is right here at 0, 0, 0. We're going to have to go 1 foot this way and 3 feet this way. And what we want to do is we want to write the force along the line as a Cartesian vector. So a Cartesian vector means we have I, we have j, and we have k components. And we also want to determine its angle. So we're going to want to figure out the force. And by determining its angle, we're going to need its alpha, its beta, and its gamma angles. So it's directional cosine angles. So we have this force we have this line. We know the magnitude of the force. So we do know this part. We know this F. Now we need to figure out what what our position vector is. So all we want to do is find the different parts of this equation. How I typically do these problems is when I see a point that's interesting, sort of A, and this point over here, let's call this B, I like to write out the X, Y, and Z locations of these points. So in A's case, I'm at 0, 0. I'm not moving this way. I'm not moving this way. But I'm going 30 feet up. So this is going to have a 0, 0, and 30. In B's case, how do I get to B? Well, I have to go 3 feet in the X, and then I have to go, well, this is in the negative Y direction, right? This is the positive Y direction. So I have to go 1 foot in the minus Y direction. So 3 minus 1. And then I have to go 5 feet high. So that's going to be 5. So B is located at 3, minus 1, and 5. And to figure out this position vector, we need to remember we can find the position vector. The position vector is going to be the head of the vector minus the tail of the vector. And these are going to be the x, y, z position. So this would be some x, y, z minus some x, y, z. And this is going to give me something that has I, j, k components. So B is at the head of the vector. We're going to subtract A, which is the tail of the vector. So R, A, B is going to be equal to 3 minus 0, I, plus minus 1 minus 0, j, plus 5 minus 30, k. I get these values from these dimensions right here. So this is going to be equal to 3i minus 1j plus minus 25k. So that's my position vector. And that's this part of the equation. I can also figure out the magnitude. So my magnitude of my position vector is going to be equal to the square root of the sum of the squares of these terms. So 3 squared plus minus 1 squared plus minus 25 squared. This term, this term, this term. So if I perform this operation, I have 3 squared plus minus 1 squared plus minus 25 squared. Take the square root of this, and I get 25.2. So this is equal to 25.2 pounds. So now I have this term. I have everything now. I can solve for my force vector. I have my force vector F is equal to this 30-pound force times, and I'm going to write it out completely, times 3i minus 1j minus 25k divided by this 25.2. Now this can be equal to 30 times 3 divided by 25.2i minus 1 over 25.2j minus 25 over 25.2k. Now, the last thing we need to do, we need to actually perform this calculation. So to perform this calculation, I'm going to say I need to do it each for the I, for the J, and for the K term. So I'm going to have 3 divided by 25.2 times 30. So this is 3.57 I. And then I'm going to have minus 1 divided by 25.2 times 30 minus 1.19 J. And then minus 25 divided by 25.2 times 30, and that's going to be minus 29.76 K. So this is my force, and I should put some units of pounds on it. So this is that. Now finally, I want to find my alpha, my beta, and my gamma angles. If you remember, these are directional cosine angles. So those directional cosines are going to figure out where this force is in space. So if we look at alpha, if we look at the original equation for alpha, we have alpha is the inverse cosine. And then we need to look at the x component of this force over the magnitude. So this could be the, fx over x, or what we can use and we should use is this, because it points in the same direction as f. So we're going to have we're going to have the x component of this RAB, the x component over that magnitude. It's the same thing as the x component of the force, because they both act in the same direction. So our position vector is it's easier. It's right here. So alpha is going to be the inverse cosine of this 3 over 25.2. And that would give us inverse cosine 3 divided by 25.2. We get 83.16. Now beta is going to be the inverse cosine. We got to use the y. So we're going to use this minus 1. Don't forget the minus sign on these. Over 25.2. The inverse cosine of minus 1 divided by 25.2. 92.3. And then we have gamma will be the inverse cosine of, again, don't forget the minus sign. That seems to get lost a lot of times with these cosine angles. So minus 25 divided by 25.2. And that will be minus 25 divided by 25.2, 172.8 degrees. Now we can check if these were valid. If you remember, the 1 is equal to the cosine, the square of alpha plus the square of beta plus the square of gamma if we wanted to do this check. So here we need to get this to be about 1. It's not going to be exact because we were estimating. So I'll have the cosine of 83.16 squared plus the cosine of 92.3 squared plus the cosine of 172.8 squared. And so this should get me about 1. Yeah, it gives me about 1. So these are valid cosine angles. Now, hopefully this video helped you realize how to take a force along a line. And as we go through more videos, this will become an important tool that we have when working with 3D vectors. If this video was helpful, please consider subscribing to my channel so you'll get notified of new videos when I release them, or liking the video so other people who might need help will be able to find this video easier.